So, we start our course magnetostatics. We have already started it. This will be the formal lesson on this. And as you know, the magnetostatics is the area in which we study magnetic fields produced by steady currents. And steady currents means you have currents which do not change with time. Those currents are known as steady currents. So, for example, if I take this pipe and rub it on a cloth, you all know what happens. There is some electrons transfer from one material to the other material, and if you rub, then you get surface charge on this pipe. On this pipe you have charges. Also you have charges on the cloth. So, you have charges here, and if I move my hand like this, charges are in motion, and charges in motion make the current. That is the very definition of current. What is current? Charges in motion, they make current. So, yes, there is a current, and that current produces magnetic field, fine, but this is not a steady current. Even if I move it with uniform velocity, it is not a steady current, because at certain time when the pipe is here, the charge is here, charge is moving here, and therefore there is a current. Then the pipe goes here, and here that current becomes 0. So, current depends on time. When the pipe was here, at that time there was a current, and then when pipe went ahead, the current became 0. So, current is changing with time. So, this is not a steady current. But suppose I rub it in a proper fashion, so that there is a uniform charge density everywhere on the pipe, okay, some sigma everywhere on the pipe, and if I rotate the pipe at its own place around this axis, if I rotate the pipe around this axis with a uniform angular velocity, imagine there is charge everywhere on this pipe, here, 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 and the charge density is also same here, 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 and then I am rotating it about its own axis like this. Is there anything changing with time? At any place the current which is there, if there is a charge, there is a current. If there is no charge, outside the pipe, no charge, no current, or inside that hollow region in the pipe, there is no charge, no current, fine, good. If it is 0, it remains 0, and if the charge is there and it is moving, it is rotating, then at any other time the same charge density will be there, and same velocity will be there, same motion will be there. So, this will make a steady current. Okay. So, whenever currents are time independent, then we say that it is steady current. Now, currents as you define, I is equal to dq by dt, but what is this dq and what is the dt? In calculus, when we say dy dx, that means when x changes by some value, then y also changes by corresponding value. So, what is that q and what is that t? Here the interpretation is slightly different. Normally we will have current on the materials, but not necessarily. For example, suppose I have a accelerator, you know the accelerators, you have accelerators, you must have heard Large Hadron Collider. So, it is an accelerator which accelerates ions up to large velocities. So, you inject some ions, and these ions are accelerated, and then they gain large velocity, and then come out with this accelerator with velocity, and then they move, and whatever experiment we want to do, we do it here. So, if I look at this place, now they have attained a velocity, and then therefore they are moving, there are charges, they are moving. So, there is a current. This current is not sitting on any solid block or any material. So, these kind of situations are also good enough to produce magnetic field and everything, but generally the currents that we will be talking or we have in mind is current which is on some material. For example, if I use this wire to make a circuit, and then the current is going, then what is happening? Inside this plastic, red plastic, you have a copper wire, and in that copper wire, that is the material, in that copper wire, okay, so this can also be taken, this picture, but let us say this is a wire, piece of a wire, copper wire, metallic wire. It has positive charges, lot many positive charges, and also the electrons, right. This copper wire inside, it has many those copper ions and the electrons, copper nuclei, let us say copper nuclei. Then you have the inner electrons which do not take part in the current, and but then you have outer electrons which are somehow, because of the interaction of different atoms of the copper, they are almost free to move everywhere in the wire, right, and we call it conduction electrons or free electrons. There are a lot of free electrons, perhaps one donated by each atom, and the number of atoms in this wire you can estimate. It will be a good exercise. Take the atomic weight of copper, and what is the length, what is the area of cross section, what is the density, how many atoms are there, from each atom one electron is coming out, so how many conduction electrons are there. So those electrons which are there, they are ready to move. So current is given by those free electrons which are there. The electrons which are bound, that 1s 2s, they will not participate in the current, but the positive nuclei of copper nuclei, they will not participate in the current. But if you apply some electric field, if you connect it to some battery, then these free electrons, only they start moving, okay. So for discussing current, we can ignore all other things, although is there positive charge is there, the inner electrons are there, but only look at the free electrons. So if rho is the density, charge density, okay, not mass density, charge per unit volume. So this will be dq divided by d tau. These are the symbols that keep learning. This d tau I will always use for volume element, small volume, tau, the Greek letter tau, d tau. So if I take a small volume in this wire, suppose this is a wire and I take a small volume d tau here, and in that d tau, how many free electrons are there, right? How many free electrons are there? Look at only that charge, and that charge divided by that volume is the charge density of the charges which are contributing to the current. So if you have a charge density rho and then it moves, then you have a current on that. Okay, then there is a word which is called current density. And what is that? Current is measured across some kind of cross section. How do I know what is this dq and what is this dt? Come back to this question. What is this dq? This dq is, you first decide a cross section, an area in your wire, and then ask how much charge has gone from one side of this area to the other side, right? So if you have a wire, then in this wire you take any cross section, and need not be the full cross section, you can take small part of the cross section also. So construct that or imagine that cross section and then ask how much charge has gone from this side of that area to the other side. How much charge has crossed this area that you have imagined. So the charge which is crossing this area in time dt is this dq. Okay. So understanding the equation is very important. Remembering the equation is important, but more important is understanding the equation. So this dq is the charge which goes from one side of the chosen area to the other side in time dt, right? So if you have let us say you have this wire, Suppose you have this wire and then you take this cross section. You take this cross section, and this is let us say delta A. And if dq charge crosses, the charges are crossing, and remember we normally write everything assuming that it is positive charge, but our equations are equally valid if the positive charges are crossing or the negative charges are crossing. Okay. So, if dq is a charge which is crossing this area in time dt, then your current is dq by dt, and this I divided by delta A, this is known as J, and this is called current density. So, the density word is coming before with different meanings. When we say charge density, we talk of a volume, how much charge is contained in this volume. When I talk of current density, then how much charge is crossing per unit time, per unit area of the cross section. Here you can say that it is how much charge is contained per unit volume. Here it is how much current is crossing per unit area. So, current crossing divided by this delta A, that is J. And if you are, I hope you are aware of this vector. If this is an area, you can define an area vector. If it is not a closed area, then you can decide the direction of delta A yourself, this way or that way. So, whichever way is the current, take that as the direction, and if you call it this delta A, and then the current density is also given the direction, and the direction is same as the direction in which this current is going. And so, if this is your current density, then you can write this as J. Current is this J dot, or let me write capital J, vector dot delta A, vector delta I, let us call it delta I. What is this? What is this? What is this? I say that I am defining a current density. The magnitude of the current density is given by this equation. This is the current density J, I divided by delta A. I is the current which is going from this side to that side, that means dq charge going in time dt, and then I divide and get I, and then I ask how much is the total current, how much is the total area through which this current is going, divide by the area, that is the current density magnitude. And the direction of the current density is same as the direction of the current. Now, this is point by point defined, point by point defined. Here how much is the current density, here how much is the current density, here how much is the current density, here how much is the current density. And with that point you can construct a smaller area also. You can construct a small area here because it is delta A, your wire may be thick enough, okay. So, you can make a delta A, small delta A if you so wish, and then the charge which is crossing, dq dt, I divided by delta A, all those things you can do here, and you can make this area small, 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 very small. Okay, this is another thing. When I say very small in this course, right, it has to be understood very clearly that we are talking of length scales or area scales or volume scales in which there are at least 10, 15,000, 20,000, 50,000 electrons or equivalent charge. We will not be talking of angstroms and nanometers, right, then it will not be classical, it is classical electromagnetism. So, whenever I say that I am taking very small infinitesimal volume, we still are not talking in terms of angstrom nanometers, at least micrometers. So, that is our small. So, that way you define this J, and then this J dot dA, magnitude of this into magnitude of this, J into dA will be I. And writing in this vector equation is gives another benefit, because this j is now point by point it is defined. If you are here, construct the area here. If you are here, construct the area here. You are here, construct the area here. So at every point you have its own j, and this delta I is through that whole cross section, this cross section or this cross section and so on, this cross section, whatever cross section you make, whatever area you make. And if the area is slant, no problem. This is delta A, this is delta A, this is j. J dot delta A will still give you the current. So let me take a case, and that is, suppose you have a wire of some cross sectional area A, okay, and then you have rho, this is the charge density of the charge carriers. That means if it is a metallic wire, it is basically free electrons. So this is rho. Or if you have put the wire somehow, put the charge somehow on a material, then whatever is the charge per unit volume, that is this rho. So rho is the charge density, and this rho, this charge is moving with a velocity v of the charge. Okay, so this is the velocity direction. So you have charges, and all the charges are moving in this direction, and total charge per unit volume is rho, and we are asking how much is the current or current density. So we can do it. Consider this cross section here, and then take some dt time and construct a length Vt. This is, let us say, V into dt, this length. So rho is given, V is given, and then we consider some time dt, and then V into dt will be a length. So here is one cross section, and behind that, okay, V dt length, behind that I take another cross section and look at this wire at a certain instant t. Okay, at one instant t, at time t, what is happening? At time t, this charge is here, this charge is here, this is here, this is here, this is here, this is here. At time t, how much is the total charge? How much is the total charge at time t contained in this cylinder? So that charge, let's call it delta q. That charge will be, this is area A, then this is length V dt. So this becomes the volume and multiplied by rho. Rho is the charge per unit volume. So this is the volume, and rho multiply, you get charge delta q. It's not this dq, it's not flowing in time dt. This charge that I am writing here is the charge contained in the cylindrical volume at that time t. Now think what happens in next time interval dt. In next time interval dt, which charge is where? So look at these charges which are right here on this cross section. These charges, how much distance they will travel? They will travel v into dt distance, because v is the velocity, dt is the time I am allowing. So each of these charge will be here. Each of these charge will come here. Okay, and if this charge has come here, then all these charges, where are they? They have crossed this cross section in time dt. If this charge has come here, that means all these charges have already gone, right? So in time dt, how much charge has crossed this? And anything behind this has not yet reached here. Anything behind this charge, these charges these charges are still somewhere here. I am looking for how much charge has crossed this particular area in that time interval dt. So only these charges have crossed, only these charges have crossed, and all of these charges have crossed. So how much charge is crossed, that we have already written. It is the charge which was contained here at time t, only that will cross here in next dt, and therefore this is the charge which has crossed this cross section. So how much is the current? How much is the current? The current will be A into V and into rho. And how much will be J? J will be current divided by that area, and that will be rho times V, and I put a vector sign. The direction of this current density, now I have current density. The direction of this current density is it's same as the direction of this velocity V, provided this rho is positive. You know that. If I write some vector as minus I cap, if I multiply it by a negative quantity, then the direction of A vector is opposite to the direction of this I cap vector. If this rho is positive, good. Whatever is the velocity direction, that is the same as the current density direction. But if this is this rho is negative, then this J is opposite to the direction of the velocity. So if it has electrons, then the current density and hence the current will be in the opposite direction. And if it is positive ions or positive charge, then they will be in the same direction. This equation is valid for both of them, right? So keep this in mind. We will be using this many times. I have taken the entire cross section, but the same thing can happen if you take a small cross section, very small cross section. Then also you can make a cylinder of this length v dt, and the same thing, same equation will cover. And therefore, as I said, this is a point by point quantity defined for a point, defined at a point x comma y comma z, right? So that's the relation J equal to rho v. We will be using it, and this current is known as current means this current means the current that we are talking, and generally that will be the case. I have a wire, I have a material, and then the charges are flowing, and then I take a cross section, divide. So this is also known as the volume current density. This current is known as volume current, and this J which I have calculated is known as volume current density. Okay, so we will stop here, and we have put this adjective volume current and volume current density because I will also be talking of surface current and surface current density next lecture.